Okay, so firstly, I think I still have very few students who have contacted me about the project. So I do encourage, because you have to send me your initial sort of selection of the project by this Friday. So to encourage that, I'm going to have a long extended office hours today. That is from after the class all the way to 5 p.m. So just come by. I'll probably just go out for lunch, maybe uh, around 1 p.m. or so, but otherwise, so this is your chance. Unless you start discussing with me, there is no way you're going to select.
When are you going to post the questions for the abstract?
I'll do it probably later today, but basically they will ask you what's the title, what's the team, what material do you need, what you hope to accomplish. It's going to be a very simple set of questions. It's not a very elaborate kind of proposal or something like that, okay? And you guys are set, so other than I need to get you the USB stick. But, okay, so please make sure to connect with me today for sure, so that we can discuss the project ideas. Okay, so continuing with this discussion of thread and events that I had started last time around. We kind of saw there are different ways you could organize the software. So very simple single program, you kind of essentially write a infinite for loop and call functions within it in some fashion. And we saw some limitations of it, that for simple stuff is fine, but for complicated stuff it creates problems. Then we moved to a model where you make use of the fact that hardware provides you interrupt handlers, which is a form of concurrency that exists at the hardware level. That is, you could be running something and the interrupt handler can fire up anytime, do some stuff, move on. So you could always structure systems where there are two things going on in parallel, or more than two if you have multiple interrupts. And that begins to lead to kind of ways of organizing things where you have multiple things going on at the same time, which is something which is very common in embedded systems because you have many different sensors. So we were discussing that when it comes to multiple things, there are some hardware-oriented ways to organize it. One is map everything to a different processor and then connect them through some communication mechanism. Another one is to map most of all the externally triggered stuff to interrupt handlers, and then have this background task which kind of does kind of the non-real-time stuff. Interrupt handler should be very quick to return, otherwise you're going to block the whole system. But more generally, I mean, those approaches are kind of constraining. So more generally, you would organize your system at the software level. So imagine now you're writing a program that has to do multiple things. Keep tab on multiple events that are coming. So threads is one way. You think of your program as multiple logically independent thread. Each thread is doing a task, and these threads kind of interact with each other by sending some data to each other. But so, like for example, if I'm designing a system for a car, I'll need something which is monitoring the brakes, something else which is monitoring the nav unit, something else which is, let's say, looking at the steering wheel, and maybe radars at the back and the front, things like that. If you were to shoehorn everything into a single program in a single for loop, or write it as a single thing, it kind of gets complicated. So threads let you think of each one of these as separate stuff. Within each thread, you would follow kind of a sequential logic. But then these threads interact occasionally with each other, like maybe data captured by one is sent over to another. Event handlers, on the other hand, is an approach which is closer to our multiple interrupts approach, except now you're doing it at the software level. So somewhere in software, you're going to maintain a queue saying what events have arrived. Events are things coming from outside, or maybe that your software generated. So it could be like a timer fired, or sensor has given an event that someone entered a room, things like that. So event could be fairly diverse in nature, and kind of the idea is you write a program in a fashion where you say wait for the next wait for a set of events, and then if an event has arrived, call the corresponding function, and it's truly a function, so you'll wait for that function to finish, return, then you again look at your event queue to see if there is something else. So this kind of style of programming is very commonly used in things like graphic user interfaces. So every mouse click and things like that really is an event, goes and sits in the event queue, and you structure your program as a set of functions which are bound to those events. So like you may have an event to handle the pressing down of a mouse button, another event to handle perhaps the mouse button being released, another button for the mouse being moved. Equivalently, in embedded system context, these events could correspond to events coming from sensors. So these are two kind of stylistically different ways of organizing things, and as I mentioned last time, that both are used. They have their pros and cons. Generally speaking, you would see that a single thread, because it just only worries about what that thread is doing, is usually very easy to understand. There's a set of steps happening, like wait for an event, process that event, generate some other event, take some action. And so within a thread, you will only concern yourself about what that thread is responsible for. And other threads do their own tasks. And then there is very explicit communication between them. So it tends to be easier to understand. It sort of tends to be clearer what the programmer wants. But all of this comes at the cost, because we have to transfer control back and forth between threads, and that means you have to do what is called as context switch, which means somehow the operating system has to stop a running thread, save its state, start another thread, and then when that thread hits something where it is waiting for something to happen, then you have to kind of repeat the whole process again. And all of that kind of requires additional overhead. The other thing is that if you mess up the communication between threads, namely, let's say there is some device which is such that if once you started using it, you have to, let's say a thread started using, giving command to an actuator. Then another thread should not come and start writing to the same actuator. So you have to lock the actuator. And if you mess that up, problems may happen. And also, the other thing we kind of realized was that since each thread is kind of an independently running logical entity, it needs its own stack. So if you have small amounts of memory, that can kind of become a problem also. So threads work great when you are running a relatively general purpose operating system like Linux, or similar complexity embedded operating systems. But if you're running on tinier things like embeds and all, you could do threads, and there are thread type operating systems and packages, but they do come at a cost. Event-oriented programming, on the other hand, is all it requires is making function calls. So all you have to do is maintain a queue. You will have some data structure called event. There's a queue of these events. Those events can be generated by two places. One is your interrupt handlers. Whenever an interrupt comes, you will do a very quick and dirty handling of that, and then create an event data structure and put it into that queue. Your background task, all it is doing is it's kind of sitting in a loop. It says, is there something in that queue? If so, call the corresponding function. If not, it will just wait until something comes into the queue. Two things can put stuff into that queue. One is those interrupt handlers that I already mentioned, and the other is an event handler can, the function that you call, in turn can generate an event. So for example, let's say I had something where I'm reading stuff from a sensor, and then I want to, when I have enough samples, I want to do some computation over it. Let's say I want to do an FFT. So then the reader handler will collect these things, and once it knows there is enough sample, it will generate an event to activate the FFT handler. So you may have events going from one handler to another handler. So that's kind of a style of event-oriented programming. Most simpler packages, Arduino, Embed, and all really kind of follow that model. Okay, they may expose it in different ways, but fundamentally that's what they're doing. They tend not to go after this model because here you just don't have enough memory. We are dealing with processors with tens of kilobytes of RAMs. But this does come at a cost. So while it gives me performance and the overhead, it comes with cost. So first thing is that it's very hard to figure out what sequence the handlers are running in, because that depends upon the sequence in which the events arrived. So if you were to be, so I may have, let's say, a bunch of functions corresponding to the handlers. They may get called in an arbitrary sequence depending upon what was happening in that particular situation of the system. Whereas here, if I'm looking at a single thread, it is following a very linear flow of control, which is tends to be easier to understand. You cannot pass state from one handler to another handler, because these are function calls. So if you want to pass some information from one to another, you have to explicitly maintain some data structure outside these handlers, because any data structure you create within the function goes onto the stack. When you return, that's lost. So in languages like C and all, you can declare a data structure within a function to be static. What does that do?
Maintains its value during subsequent calls.
During subsequent calls. So in a function, if I were to write, like, not very commonly used, but let's say I have a function, whatever f, and then normally I just say int x, right? And or could be anything. That just goes into the stack, and then when you return, this is lost. But I can put static, and now what it does is it puts it outside the stack in some global area of memory, so that next time this function is called, the value of x was what was left on the previous occasion. But that is not entirely satisfactory either, because there's a single copy of x, which means if two different entities are, so that means all calls to f share the same x. But oftentimes what I may want is that two different people may be using f, and each one of them want their own personal copy of x, right? I mean, I have an ff, let's say I have some function where next time around I call it, I need to make use of the same state, and you are using the same function, then this approach won't work. What that means is both of us have to now maintain our own copy of the state, and then the typical usage then becomes function f, and there would be an argument which corresponds to the state. And it becomes the user's responsibility to maintain the state and then keep passing it every time. And this function will modify that. Let's say, what would be a good example? Let's say my handler internally has a finite state machine, okay? And a finite state machine needs to know what its current state is. And next time all my handler does is every time I call this handler, I pass to it the new event that has come, and then based upon that, the handler internally has to change its state. Well, and you are using the same handler, and you're using the same state machine, but it's a second instance of the state machine. Then both of us have to, the current state would be the variable that each one of us will have to maintain, and then pass it around. That tends to get very kludgy with events, because questions come: who maintains this? Where do you maintain it? It's not a very clean model. So passing state or having handlers which have state is very tricky. If, on the other hand, each handler runs to completion and there is nothing that needs to be remembered, it tends to be a funny model. No way to exploit CPU concurrency cleanly, because one of the assumptions behind this model is that handlers run in a sequence. That's the nice thing about this model. That is, it's never the case that two handlers are running simultaneously. You are guaranteed that at any given point in time, it's as if a single handler is running. So I don't have to worry about all these things like with shared resources and all that normally I would have to worry about in the thread case. But what this also means is that if I have multiple CPUs, it's not as if I can run, if I have two events in my queue, I can just blindly run a handler in one queue, one CPU, and the other handler, which is also ready, in the second CPU, because now they may run simultaneously, and I'll have the same set of issues that we are facing out here. It begins to look like threads. So event-based approach really works well when you have a single CPU, which is certainly true for a lot of embedded systems. In fact, most embedded systems tend to be like that. But the moment you have multiple CPUs, you have to begin to get careful. The final one is the following, which is listed out here. That is, I have to explicitly register or deregister every handler. So let's contrast with, let's say I am engaged in a protocol. A very common protocol is one party requests something to be done. The server handles it. It goes back out here. Then maybe a follow-up request comes. So let's say I expect from some sensor a sequence of 2 events. I would first get from it event 1. When the event 1 comes, I'm going to do something, and then I'm going to respond to the sensor, and then it will send me event 2. In thread, what I would say is wait for event 1. When the event 1 comes, then I'm going to do something. Then I'll say wait for event 2. So when I issue the command wait for event 1, I'm only looking for event 1. If event 2 happens to arrive for whatever reason, or any other event arrives, I'm going to ignore that. And then when event 1 does come, then I process it, and then I tell the operating system, now wait for event 2. So what is happening in this kind of situation is that at the set of events that I'm waiting for and that I'm going to handle is dynamically changing. Here, what I'll have to do is I'll have to say event 1 handler is function 1. Event 2, event of type 2, handler is F2. And if it so happens that I get an unexpected event at any given point in time, then the corresponding handler will get called, and then I have to make sure in the code that it knows that it is not expected and returns without taking any action. So like if I was in a state where I'm waiting for event 1, but event 2 happens to arrive, then I should ignore it. So there are a couple of things out there. Number one, I'm forced to handle events that I don't care about. And second thing is it complicates the handler itself. Because there is no such concept as saying that I'm in a certain state and I only want to listen for some events. I have to declare all these handlers up front unless you want to complicate your code a lot and do dynamic registration, deregistration of handlers. And then by that time you begin to look something like threads anyway. So events work well where, the way I like to think of it is events actually shine where if you were to be logically thinking of your system like a finite state machine, if you were to think of your embedded system as write it as a single state machine, in a finite state machine, you do know one property holds. You are in a given state at any given point in time. You cannot be in multiple states. So it's a strictly sequential kind of a system. And then when events come, you jump from state to state. That's the kind of system where these things work very well. This thing works very well when you have multiple finite state machines. And each one of them you are thinking logically differently, and that each one of them may map to a separate thread. That's kind of one way of thinking about it. Having said that, so these complementary advantages, disadvantages, there are packages which are operating systems which really are event-oriented operating systems, but they try to hide the fact and make it look like thread, and we'll see a couple of examples shortly. So thread and event, it's kind of a big sort of, there are camps on either side and there are kind of issues on either side. So programming with threads kind of requires you to essentially have a more complicated operating system. It would have a concept of a process or a thread, and the operating system will maintain the stack and other state relevant to that thread. And a very common model, which we'll see in the next slide set, is that what you normally do is that you would declare, you'll tell the operating system something about what's the nature of the thread, how often it is activated. So one model of a thread is that I spawn off a thread, I start a thread, and then it keeps running, and at some stage it is going to return, and I may write a thread which just keeps running always. So within the thread, I will have something waiting for an event to come, process it, do stuff like that. A second model which is used is that threads are finite. So within the course of the runtime of my embedded system, the same thread may get called again and again. So an event comes, I fire up the corresponding thread, that thread will run through its course, finish, exit. Next time the same event comes, I'm again going to fire a copy of the thread. And a very common model in that case is that the threads could be viewed as two types: threads which are coming periodically because the event is coming periodically, or the threads arrive totally asynchronously. So threads may have constraints on them. How often they come? When they do come, I have to make sure they finish. So for example, it could be that a thread, I have a sensor which generates an event every 10 seconds. And I may have a constraint saying that every time an event comes, I have to make sure I finish handling it before the next copy of the same event comes. Okay, so that's an example of a time constraint. Or it could be that every time the event comes, I need to finish handling it within 1 millisecond. There could be these kind of constraints which are specified, and a lot of real-time systems are really about making sure that we meet those timing constraints. There may be other issues, like for example, threads may need resources. Like I may have a thread which needs the radio, and I may have a second thread which also needs the radio, and I have to make sure that both are able to kind of handle things. Threads may have importance. Like let's say I have multiple threads ready at the same time. I may tell you that this one is more critical because maybe it's handling the brakes versus the other one which is handling, let's say, the nav unit in the car. So there could be criticalness or different priorities associated with them. Threads may have a producer-consumer relationship. That is, one thread may produce input needed by a different thread. And communication and timing requirements. So internally, what operating systems do is they think of a thread to be in one of several states. One is the thread is ready to run. If I were to give it a CPU, it's good to go. Another one is that internally the thread has made a request and I'm waiting for that to be fulfilled. So for example, a thread may have said, wait for an event from a sensor, but no event has arrived. So now the thread is in kind of a waiting mode. So there is a second state for a thread, which is kind of a waiting for. And then, so those are called blocked, waiting for some event. And the other one is they're otherwise ready. Only thing is they're waiting for the CPU. Other examples of waiting for something could be like, for example, so I gave the example of waiting for an event. It could also be, I need the radio, but some other thread has the radio right now. So I have to wait for that other thread to release the radio before I can use it. So I'm waiting for something, or I'm waiting for the CPU. These are kind of two very broad modes. And of course, if there is a thread ready to run, then there would also be a running thread, which is currently has a CPU. And what all the OS is really doing is, whenever the running thread hits a call where it has to now wait for something, then this running thread exits or whatever, temporarily exits, and the operating system will give control to one of the threads which is waiting for the CPU. So that's one condition where control transfers. A second condition under which control transfers is following. I have a thread currently running, but now an event comes, and this is a very high priority critical event. I have to handle it, and if I let the currently running thread continue, I will miss the deadline. In that case, the OS will intervene. It will tell this thread, it will preempt this thread, so that will be moved to waiting for CPU queue, and I will start running the new thread. So all of this process is what is called scheduling. And the next slide set, which I posted this morning, deals with this issue of how can we do scheduling while meeting the timing constraints. That's kind of the usually kind of the hard thing in embedded systems. So that's about the task characteristics. And as we saw, within that, there is this issue of how do we schedule. So one thing which distinguishes non-real-time type systems from real-time type systems is that in non-real-time systems, the operating system, the only promise it makes is that I will run the threads in a best effort fashion. I make no guarantees about meeting any timing constraints. So usually what these operating systems, and Linux is a good example of one, what they strive for is, number one, CPU is a precious resource. Let's try to keep it busy. So I want to maximize how much work I can do. And the other thing we try to do is they try to be fair, that it is not good if one thread is locked out forever. So it should make some progress, but no guarantees otherwise about how one thread would fare versus another. So let's take an, do you think it would ever be useful for an operating system to keep a CPU idle even though there is something ready to run? Can you imagine a scenario where I have threads which are good to go, they're waiting for the CPU, but I deliberately decide to keep the CPU idle?
Well,
Anthony?
are you trying to save power so the battery doesn't run out?
Yeah, although I will have to run those threads eventually anyway, so it doesn't quite help with the power the way you are saying, but it can. Maybe some.
Maybe waiting for some other more priority threads that will arrive in the future.
Okay, so that's one scenario. So what Mustafa is saying is the following, that let's say there is a very high priority urgent task which comes every second. And it has to be handled very quickly and all. And right now I'm just a millisecond before that 1 second mark. I have something good to go, but if I am a non-preemptive system, as in once I give control to the CPU to this thread, I'll have to wait for it to finish, then I'll miss handling this critical task. So there are times at which you can deliberately leave the CPU idle because even though there was something good to go, because I'm expecting something high priority to happen. So this kind of approach where something is good to go, but I'm not running it, is called non-conservative schedulers. That is, they may leave a CPU or a resource unutilized, even though it could have been utilized by some task. So that's one condition. Now let's think about what Anthony said, something to do with power. So one thing you would notice is that, so again, CPUs have CPUs and many other things, sensors and all, they all have multiple power states. Broadly speaking, they have an active state and a sleep state. The problem is that going from active to sleep and back does cost additional time. So like I have to spin up the disk or power up the clock or kind of sort of reboot the operating system, all these kind of things. So let's say I have a tiny little task which is good to go. Should I wake up the CPU, process it, or should I wait for a few more tasks to come in and then handle them in a bunch? I may be better off doing the latter. So that would be kind of the power related reasons. I still have to run it, so I'm not going to save on the active power, but I will save on the cost associated with wake up. So last slide set, we had looked at that how some processors can have very long wake up time and all. Some of the resources like if you have a true disk, not a flash drive, but like a mechanical spinning drive, they can take a second or two to spin up and kind of a big spike of energy. Radios take time to synchronize with the base station and also there are a lot of things which for waking up take extra energy, extra time, and it's not a, so you might want to sort of bundle things up. So additional complications can come. Go ahead.
I think there is another algorithm that if you have a periodic task, they make the task at the end of the period in order to have better response time for sporadic task and the periodic task.
Yeah, you are kind of jumping way ahead. Okay. Yes, so there are other reasons also because of which I can keep the CPU idle. What Amr is pointing out is that that in case I mean, it sort of falls into the first category of what Mustafa is saying, that I may delay handling a process, something because I'm kind of worried about responsiveness of something else. So broadly into the same category. So scheduling refers, so for threads, one thing that matters is the characteristics of the threads, what kind of constraints, and the second thing is how am I doing the scheduling. So best effort is what general purpose stuff do, and then there are operating systems which make guarantees. They may either make a statistical guarantee or they may make a hard guarantee. So statistical guarantee would essentially say, on an average, I'm going to make sure that you get so much. But for any given instance of the event that you're handling, I don't make that promise. So this works fine for multimedia kind of stuff, like if I'm handling audio, video, these kind of things, where if there is a tiny little jitter happening in my handling of it, human beings are reasonably tolerant of the stuff, so it might be fine. On the other hand, there are situations where things are very hard deadline, like very high quality media or like robotics or these kind of things where timing constraints would be very hard. So in which case a more deterministic thing is needed. Of course, nothing in the world is deterministic in the sense that when a CPU says that, when an operating system says, I guarantee a second latency. All that means is, and if nothing else goes wrong, like the hardware doesn't crash or the temperature doesn't go up too much or things like that. So there's always a tiny probability of failure. But the idea is that if my set of assumptions about hardware hold true, then I am going to be promising that I meet certain latency. So statistical versus deterministic, and within that, there are additional complications, like, for example, could the program be such that it may, in the middle of running, suddenly introduce a new type of thread, okay, which I didn't know about, and now suddenly the system which was running fine may actually begin to not work fine. So another major complication which sort of tends to when we start looking at kind of some of the scheduling algorithms, there are things that we don't know how to handle very well, and they become an issue in embedded systems. So for example, tasks interact because they kind of use resources, common resources and all. That's a source of complication. For example, let's say two threads, both need the radio, and I gave the radio to a thread, and it was an unimportant thread, and now it is using the radio, and now this other critical task becomes ready. It needs the radio. It has to wait for this guy. Okay, so a high priority guy, maybe a thread, may be locked out by a low priority one because it has a thread. And it's a source of constant problems and some very high profile failures that have happened to kind of major missions like Mars mission and all have been because of bugs like these. Okay, processor overload. This has become kind of a serious issue. So we grow up thinking of processors as being something where I tell them to run at a particular frequency, and that's what they're going to run at. Modern processors are not like that because we are pushing the limits quite a bit. So they have like thermal sensors in them, and if the processor begins to heat up, a governor in the hardware level is going to slow down the processor, whatever you may have told it. These kind of issues complicate things also because processors, or generally speaking our systems, are no longer deterministic. There is a lot of runtime control which the hardware exercises, and that creates kind of variations in what you see it. So this variability is a important thing, and unfortunately it's sort of inevitable because if you were to try to give a very deterministic view of hardware performance to the software, it would come at a huge cost because I'll have to be very conservative. I'll have to say, okay, I'll have to assume the worst case operating condition, worst case task set, and therefore say, I don't want my processor to ever hit that thermal limit, and therefore I'm going to run very conservatively. That doesn't really pay well. So the strategy nowadays is that we'll push the limits of the hardware, but then provide these controls at the hardware level so that when things begin to go bad, thermal runaway, these kind of things, that the processor is at the risk of causing damage to itself, we slow down, irrespective of what the software may be saying. So software now gets kind of a stochastic view of the hardware or a non-deterministic view of the hardware. So again, going back to my point, there are no guarantees. Eventually, you have to carefully kind of design around these things. And these kind of overload condition and all sort of happen. In fact, many of our devices have this thing. Once they hit the thermal limit and all, they begin to shut down, slow things down and all. One key distinction between different implementation of threads is, are threads preemptible or not? So preemption means that a running thread could be stopped by the operating system irrespective of what the thread is doing. And non-preemption means that only when the thread decides to give up control would the OS intervene. Okay, so in a preemption, in a non-preemption case, the only thing which can interrupt a thread are the hardware interrupts, nothing else. And it's also possible that the thread may lock out the interrupts. It may say disable the interrupts. So preemption is a little bit like event handlers in the sense that I cannot stop the thread in the middle. The distinction is it's still not a function call. So a thread may there are certain things that calls that a thread may make, basically system calls to the operating system, which is when control goes back to the OS. So like, for example, when I attempt to read from a sensor, or when I attempt to write to a file or make use of the network, these are the calls that I'm making to the operating system, and those are the points where the OS gets the control. Whereas in a preemptive case, I may be in the middle of some computation and the OS can stop me. Now, of course, preemption has the advantage that I can give control, I can handle something more important, but it has the disadvantage that I need to take care of this context switch, which is more expensive. So preemptive basically means I can stop the task in the middle at any point in time, not just at those selected kind of cases. So preemptive is kind of the more common approach you would see in kind of embedded operating systems, but there are times at which non-preemption can be beneficial too. Non-preemption gives me more control. I don't have to worry about any other thread using the same resource that I am, so it kind of does simplify things. Most common way of scheduling in embedded systems, as opposed to embedded operating systems, as opposed to, let's say, Linux type or Unix type general operating systems, is the so-called priority-based preemptive scheduling. And the basic idea out here is I have a bunch of threads. I'm going to give each one of them a priority, and then my operating system and I can preempt threads and all, and the operating system follows a very simple rule. If at any given point in time the CPU is given to the thread which has the highest priority. So if I'm running a thread and a hardware event happens, and as a result of that hardware event, a new thread becomes ready to run, and if this thread has the higher priority, then I will bring that into the CPU. So very simple rule out here. Threads have priorities, and at any given point in time, I'm going to run the highest priority thread. And therefore, the scheduling problem is one of saying, how do I assign those priorities? Are there ways of assigning this priority that will help me meet the time constraints? Two very broad, one dimension in which you can think about it is, do I assign these priorities upfront, or can I change these priorities dynamically? So upfront type approach, very simple to implement. So at the time of writing the program, I have to, whenever I say create a thread, I would also say create a thread. I'll somehow tell the operating system before it even begins to run my threads that I have these many threads and these are their priorities. And the OS from that point on will just assume that. Dynamic priority thread means that I can keep changing the relative priorities of the thread. So thread A may have higher priority than B right now, but that may change later on, and it's kind of a more complicated thing. Why might I do dynamic priority? Well, because it can help me be more responsive. Maybe I can handle tasks that I couldn't otherwise. Linux type operating systems do not do this. So anyone knows about how our general purpose operating systems handle things of different priorities, if you may, or different threads? Hmm? What do you mean by aging?
They decrease the priority of the threads for a certain amount of time to prevent the task with the lowest priority from.
So they do have priorities. Okay, anyone knows about this command called nice? Ivan, what does it do?
So in the Linux kernel itself, the niceness is an index of measure of these processes that are running together. So together with the same concept of time, if you are running for a pretty long time, your niceness index gets adjusted. So there will be a scheduling based on this priority of niceness for each of these processes within the kernel.
So, okay. So, sort of right on, but let me kind of rephrase this thing. So you'll hear about priority in general purpose operating systems, but that's not this. Here, remember, priority has a very specific meaning. Namely, at any given point in time, the thread which has the highest priority will have the CPU. In general purpose operating systems, there is no such guarantee made. Instead, priority is used to give that over long time, which thread may get more of the CPU than the other one. So for example, if I ran some kind of heavy duty MATLAB computation in the background and I don't want rest of my system to slow down, I can lower its priority, okay, so that my interactive tasks kind of keep getting more of the CPU. So what these general purpose operating systems do is they run on the concept of a time slice. Every so often there is a clock tick which comes, okay, at least that's how it used to be until fairly recently. So usually that number is anywhere from 10 to 20 milliseconds. So every 10 to 20 milliseconds, a clock tick comes. And when that clock tick comes, then the OS decides which thread or process to give control to. Now it may happen that in between this time slice, the currently running thread may now block because it tried to access a file or some device or some other resource which is not available. In which case, again, OS will get control back and it will give some control to some other thread. But otherwise, kind of things happen at that 10 millisecond boundary. And then this priority which these operating systems use is really only to decide how much I favor one versus the other. So if everyone had the same priority, everyone will have the same go at getting a chance at the CPU. If on the other hand, one is higher than the other, then I'll give the higher priority guy more chance statistically at whenever I decide which thread to pick than the other. No guarantees made about any deadlines, and as you can see, if time slices are 10 to 20 milliseconds, that in itself places a limit on how responsive can I be, because once I give control to a thread, and if this thread has work to do and will keep the next time slice fully occupied, if a new stuff becomes ready, a new event comes, tough luck, I have to wait for it. Okay, so there are no promises made. So that's a key distinction between general purpose OSs versus this. Now, going to Raspberry Pi and BeagleBone, they therefore, because of their Linux lineage, they basically are not real time. They are operating on this time slice. When I made a comment that general purpose OSs are organized like this until very recently. So one optimization that all the three major operating systems, Linux, Windows, and Macs now do is the following. They kind of say that, it's stupid to have this clock tick keep coming every 10 milliseconds or whatnot. What if I were to adapt that interval? Okay, so instead of, because what begins to happen is that I'm waking up the CPU unnecessarily, even though I may not have much to do. So depending upon the load, they may kind of change that time. But fundamentally, otherwise, I mean, they basically, all they're doing is that at certain occasions, on a relatively relaxed basis, they are going to look at what all things are there and are going to give the CPU to one of them. They do not follow this notion that priority means it will have the CPU, irrespective. I mean, that's the so priority-based preemptive scheduling is what you would see in embedded operating systems that provide threads, and they often go under the name of real-time operating systems. There are among the big operating systems, perhaps the most famous one is something called VxWorks, which comes out of a company in Bay Area, which is kind of used by kind of let's say NASA uses it, airplanes use it, and all. Okay, so that's where it kind of gets used quite a bit. There are also real-time extensions to Linux. I'm going to go over a few of them. So you can get Linux modified to provide this kind of capability. But it's not a very clean add-on, but they do exist. You can sort of an open source version and as well as some commercial variants of Linux. But the distinction really is the guarantee we are making. And we'll see, next slide said, that by judiciously assigning the priority, I can make a promise about meeting deadline constraints. That is, if you were to assign priorities appropriately, then under certain circumstances, you can make a guarantee that this task will finish before a certain time. Okay, and that's what we want in many of these systems. There are two we will see. There's one which is called rate monotonic algorithm, and there's a close cousin of it called deadline monotonic. And we'll see how it works, but basically what it says is that if I have a bunch of tasks and I know their periods, that is how often the corresponding event arrives. So like I may have, let's say, one sensor which comes every second, another sensor which comes every 1.5 seconds. What rate monotonic says is I'm going to give the highest priority to the thread corresponding to the event which occurs more frequently. So 1 second one will have the higher priority than the 1.5 second one, independent of what work they need to do. Okay, it's purely driven by the rate. A close cousin of that is deadline thing. We'll see, but it's kind of a similar property. This is a very commonly used approach and is considered to be one of the most sort of important scheduling algorithm for real-time systems. A second one is earliest deadline first assignment. And what this says is highest priority is for that thread whose deadline is the soonest from now. Okay, so for example, so the difference out here is which thread has the highest priority may change. So here the priorities, relative priorities may change over time, because suddenly, right now, a thread may have the highest priority, but then a new thread becomes ready, and if its deadline is sooner, then its priority will become higher. So earliest deadline first basically says whosoever's deadline by wall clock time is the soonest will get the CPU. So this is dynamic priority, this is static priority, as in we assign priority up front and we don't change it over the time of the lifetime of the system. Here the priorities keep changing depending upon what's happening to the system. More complicated, but we'll see it has an advantage. I can get away with a slower CPU, or equivalently for the same CPU, I can do things which I couldn't with this approach. I could handle mixes of tasks which I couldn't otherwise. One other point I wanted to make. So I mentioned earlier concurrency and parallelism. So we often think of them as kind of equivalent at some level, but they are kind of distinct, and I do want to kind of bring that point out. So concurrency refers to that I have an application or a system where I have a bunch of independently executing things, like I'm monitoring different sensors and stuff like that. I have to do those concurrently. So as long as I can handle them, I don't really care whether they're running on one CPU or 10 CPUs. Parallelism means that I truly am simultaneously executing computation. So I have multiple pieces of hardware, and I have more than one instruction or more than one stuff happening truly simultaneously. So parallelism refers to the fact that my hardware can do more than one thing. Concurrency refers to the fact that my application is doing multiple things at the same time, but that's an illusion. That may just be an illusion I'm getting. It doesn't have to be done simultaneously. So for example, if I have to monitor two sensors, a parallel approach would be I have two pieces of hardware, one monitoring one sensor, the other monitoring the other sensor. Concurrency, from a concurrency perspective, it's fine if I have a single piece of hardware which rapidly checks one the other and then kind of keeps flipping back and forth. So concurrency is composing otherwise independent things which have to sort of happen at the same time, but I arrange for it through creative scheduling and whatnot to happen. So concurrency basically means my programming language and all should have a way for me to express these things, but it doesn't mean that my hardware has to support them in parallel. So another way of saying is concurrency about dealing with lots of things at once, and parallelism is about doing lots of things at once. Okay, so there's again kind of a subtle difference. There's a very nice talk by Rob Pike. Anyone knows who Rob Pike is? You guys are too young. So Rob Pike was part of the group that gave us Unix and C and C++, kind of that set of languages. He's now at Google. Anyone heard of this language called Go? Yeah. Okay. So Go is a new systems programming language, which obviously Google is pushing very, very heavily. So you can say it's kind of the new language in the same lineage as C, C++, C#, and all. Go has some very interesting concurrency support for concurrency, and Rob Pike is kind of the creator of that Go language also. So anyway, he's one of the most famous computer scientists who has been. So just kind of interesting. So he has a very nice talk about discussing this concurrency versus parallelism, and the two are not the same, even though we often kind of confuse these things. You'll see two. Wait.
So can we say that parallelism is like multi-core CPU?
Yeah, so multi-core CPU is multiple CPUs. Now, the thing is, I may not use them that way, right? I mean, let's say I gave you a program where multiple things are happening, I may still write it as a single thread, right? I can, remember I mentioned last time around the select and poll, these kind of calls. So I may write it as check for one event, handle it, check for the next event, handle it, right? I can still write, I can deal with lots of things at once without doing multiple things simultaneously, right? So concurrency, so even if I have multiple core, my implementation may not make use of the multiple cores, okay? And most systems, you will usually have a combination of the two. That is, you will at some level decide, I may have multiple things which are truly logically independent. I don't want to mix the code base for my entertainment unit in the car with the one which is handling anti-lock brake system, okay? So I may have two threads, and then within each thread, I may organize things via the event and event handlers. So, and then give the threads appropriate priority. So you could do that way. But you're right. And the other thing, remember, is I will almost never, ever have as many cores as the number of threads I have. Okay, I mean, yeah, it's just kind of unlikely in most scenarios. Okay, embedded and real-time operating systems. So broadly speaking, embedded operating systems refer to operating systems which are relatively lightweight, can fit into small amounts of memory, may run on processors which may not have memory management units and all. Real-time operating systems, on the other hand, refer to operating systems which begin to make promises about timing constraints. Probably fair to say that real-time operating systems are almost always in the embedded category, but embedded may not be real-time, okay? You would see that there are real-time extensions to commercial OSs like Linux, I had mentioned, and certain other things. There are plenty of research and open source operating systems which are around. In some cases, your language provides support for real-time things. So Ada is an old language which provides that. There is something called real-time Java, which has notions of clocks and time and stuff like that, and which provides those guarantees also. Main issue or main thing that they differ on is what's the concurrency model? So we already discussed it. Do they provide events or threads or maybe both? How is the scheduling done? Is it static priority, dynamic priority, or is it something else? What's the memory model? Some operating systems you would see require that every data structure be declared upfront, statically. And the only thing that is dynamically allocated is the stack. So every time you call a function, variables you declare on it are on the stack. On the other hand, operating systems do allow dynamic memory are the one where you will have some way of dynamically allocating a data structure, malloc or things like that. Now in embedded systems, this tends to be frowned upon. Why? Yeah, but so what? Yeah, okay, so certainly small memory, but although one could make the case that then if I have small memory, I'm actually better off with dynamic because then I can reuse the same memory. Oh, in embedded systems, why is dynamic memory allocation, why does it tend to be frowned upon? Like you often find operating systems that don't even provide.
The real-time system, dynamic memory allocation, memory management is actually a very heavy issue because we spend a lot of time processing overhead to manage that.
Okay, there's certainly so they're processing overhead. So could you clarify further what kind of processing overhead might be there?
A lot of the problems come about dynamic memory management, not only just its allocation, because you have internal fragmentation, external fragmentation, the ability to actually move memory around just to make tasks speed up so that they can be allocated in a contiguous memory address space. So there are a lot of issues behind dynamic memory management that really in the embedded system we don't want to deal with that, especially when we're talking about real-time.
Okay, so complexity is one, which you're sort of pointing out, which is the way dynamic memory is done is I'll set aside an area of memory and then threads can come, request some chunk of memory for some time. When they are done, they return it back. And what Ivan is referring to is to manage this pool of memory. I may start dealing with a situation where my out of that pool of memory, there may be fragments that are allocated, there are fragments that are free, and to keep the whole thing efficient, I may have to kind of manage this pool actively, so I have to devote some CPU cycles toward it. that's certainly is an important point. And going further, newer languages like C# and kind of Java, these things also kind of free you up from the burden of even freeing that memory. So once I'm done using it, I can just stop using it. And then once the thread exits, or based upon some analysis, the operating system figures out, okay, I can release this thing. So that's one. But the other issue, which is more important in embedded OSs, is lack of predictability. So one thing which embedded and again / real-time systems like is a predictable system. I should be able to predict upfront that how much memory am I going to need under different scenarios, and also that this goes to the point of little memory. So I'm trying to make sure that my system will not fail through something unanticipated. So particularly on the lower end of operating systems in this space, you would see that static memory is all they kind of like to deal with. Finally, what kind of software component model do they have? Another way of saying is that do they provide you objects and these kind of things or not? And you'll sort of what's the abstraction? How do you break your system into smaller components? What is it that they support? There are plenty of standards for different industries. There is all Unix type operating systems follow an API called POSIX API. So you'll often see that my operating system is POSIX compliant, which is basically nothing but saying that the OS provides a set of function calls that you need to be able to support. So if your application assumes they exist, it will run on any POSIX compliant operating system. There's something called real-time POSIX, which basically is a set of extensions to that POSIX API which deal with timing constraints. So like, for example, priorities and stuff like that. And there are multiple variants of that API dealing with how complex a system you're dealing with. Is it a very tiny system to a kind of more complicated system? Different industries have created their own standards. So in the automotive industry, there's something called OSEC. In avionics, there's something called Apex. In Japan, came out something called Tron and Microtron. Which was more geared towards consumer electronics type applications and all. So a bunch of these different industries which have created their own embedded operating system or real-time operating system standards, catering to some of the unique needs. So let's take avionics. So avionics is one place which is probably as safety critical as it gets, okay, in the sense that you have to make some pretty hard assurances, certification before the plane is considered worthy of flying and all. So whatever you write has to be analyzable and certifiable. And the one way they try to make sure of that is by keeping things separate. And what that means is that literally the way the processor is run is they time slice the processor time. So imagine I'm running the processor where I have major time slices, and one time slice, one set of activities is happening. Then the other time slice, a totally disjoint set of activities will happen, and there cannot be any interaction between them. So temporal isolation, and then resources are guaranteed, and then on top of it, we have our fixed priority scheduling and things like that. So avionics has some pretty hard constraint. There are plenty of examples of failures that have happened because of software issues. Like, for example, the Air France crash that happened over Atlantic was partly because of a sensor issue, but there were also some software bugs which were supposed were behind it. In cars, a couple of years ago, the whole incident about Toyota's car accidentally speeding up really kind of became one, was there a bug in software? And the short answer to these things is that we just don't know, because these bugs often get triggered under situations which may not happen in your testing, may be very rare, and methodologies for us to identify when these software can fail are basically largely non-existent. I mean, in the sense, there is stuff out there, but they can handle simpler cases. There are companies which work on this thing. So if you have a very disciplined way of writing software, you have a hope. But if you just give me a general mess of a code and say, would it fail under circumstances? Would Toyota's code, does it have a bug which would explain it? Really kind of don't know. So there are, like here at UCLA, Professor Paulo Taboada, his research is about that how can I generate code which is correct by construction, That is, it is guaranteed to meet this, the constraint that the system will not go into a bad state. But the flip problem that you give me a piece of code and say, there's an accident that happened. I suspect the problem may be because of the code. Can you find it? Not really. I mean, it's extremely complicated.
Possible, right? I mean, you can just go through the running process and look line by line.
Nope, you can't. You can't, because you don't, accident happened, you don't know what sequence of events arrived.
There's a log,
And-
right? Usually there's a log.
Not at that granularity of low level. You're talking, I mean, if you're to be logging at that level every hardware event, you will just never be able to kind of do it. So replicating the conditions is extremely hard. There is not enough logging to ever kind of make that happen either. So short answer, not really, but of course, if you did, then you could play it out and say, okay, then it failed. But it still doesn't answer the question that under what other circumstances would it fail and all. So there are, not short answer, not very easy. So your strategy, which avionics says, is they restrict the way you write software. Okay, or the other approach that I mentioned, what Paulo Taboda's research does is to create code which is correct by construction. Okay, so but then you cannot create. I mean, you can only handle kind of certain classes of systems, not arbitrary kind of things. So verifying things are correct and all is very paramount in automotive and avionics, and particularly now that car companies are going with self-driving cars and all, this becomes an even more significant issue, because you may not have a human to intervene this thing at all. So within this umbrella, there are many embedded operating systems that exist, and then they're kind of organized differently. A very common one that you would find kind of at the very low end is the single program cyclic executive. The distinction partly boils down to is how much do we isolate applications from rest of the software. So in general purpose operating systems, the programs I write, barring any bugs in the operating system, I cannot mess with the operating system. And one application cannot mess with another application because they're all running in their own address spaces. Lower end operating systems, a very common organization is this. I have hardware and then everything is running on the same address space. Embed is like that. If you mess things up, then one component can write into another component. There is nothing to protect against it. And part of the reason is that without hardware support, it would be very costly to do that isolation. So, and by hardware support, I mean, is there a memory management or memory protection unit? And most of these low-end processors do not. Next up is that I do provide that separation. That is, all my operating system software is protected, and then applications run together in a different mode. So once you move up a notch of processors, you begin to see this. So some ARM processors have full-blown MMU, but there are also ARM processors which have what they call as memory protection unit. So they do not give everyone the illusion of a common address space, but you can say that this area of memory can only be written by some pieces of software and not the other. So you begin to have some protection. So some isolation between user mode and rest of the software. And let's see. So many examples. Tiny systems, probably kind of the two most famous among the operating systems at that level. Right now, I would say this thing called TinyOS, which came out of UC Berkeley, very commonly used in sensor networks and all. And then Contiki is the other one. I think these two are nowhere near the same fame. Contiki is probably the most well-known of the tinier operating systems at this stage. Mbed has gradually become, because of its support by ARM, is rapidly catching up. So Mbed OS is something which is probably also would be in this list. There are a whole bunch of others. There's something called FreeRTOS, which is very commonly used. I've seen a couple of others in kind of the same vein, but I think if I were to make a pick right now, I would say if you need support for communication and want to do IPv6 and create kind of a network kind of thing, Contiki is probably the best bet out there. If and it's a friendlier kind of environment. If on the other hand you want to interface with lots of devices and lots of platforms and all, then Embed is probably the best choice right now. These are kind of the two most, but there are other choices like FreeRTOS is also used kind of quite a bit as well. For mid-sized systems, by mid-sized systems, what I mean is I have more powerful. I begin to have more powerful processors. I could certainly run some of these things, but then certain other capabilities begin to happen, and I can have richer APIs and all. Perhaps very commonly used out here are things like various variants of embedded Linuxes. So these are stripped down Linux, which are designed to run without an MMU. ECOS is an open source operating system which is based on top of Tron or Microtron, which I had mentioned earlier. So this is made by Red Hat, the same company which makes Red Hat Linux. Micro COS is also very well-known mid-size OS. All of these provide, or many of these provide this priority-based scheduling. Micro COS 2, Micro CS 3, these are a big nice thing about them is that they come with a textbook which literally walks you through line by line of every part of the operating system. So one of the best ways to learn about an operating system is through those books. They are not very cheap. They're like $120 or so, but probably one of the best introduction to operating systems, period, and to embedded operating systems for sure. So very nicely done. They also run on a variety of OSs. They're free for academic use. So you don't even need to buy the book. You can download the code and steal the book or whatever and use it. But if you're a company, then you do have to pay them royalty. Okay, so it's kind of a mixed business model. Embed RTOS I kind of mentioned. So this is kind of a dark horse which is emerging very rapidly because ARM has put its kind of stamp of approval on it. For large size systems where you can run, which has MMUs, you can decent amount of file system space and all, you can run VxWorks, which I mentioned earlier, QNX Neutrino. This is what BlackBerry uses now. Okay, so this was a real-time operating system which BlackBerry bought. It has some very interesting characteristics. It is open source also. Various variants of real-time Linuxes, and then I guess in the same category I'll also put some of the industry-specific one I had mentioned, and there are a whole bunch of researchy kind of things that exist out there. So let's look at an example, Contiki. So Contiki, as I mentioned, is probably the most popular of the Internet of Things operating system, is how I would put it. It is in many of the commercial products that, particularly in lighting industry and all that sort of exist. There's a it came out of a university in Sweden, and then they have a company around it, which I think is called ThinkSquare, ThinkSpeak, ThinkSquare, something like that. Okay, so the main idea out here is, so it's designed for very tiny processors, even 8-bit type stuff, no MMUs, small amounts of memory. And what it really is an event-driven type of system. So the operating system, all it does is that it goes to some initialization code, and then it calls a run function. And what this run function does is, it basically maintains an event queue, and whenever the events in there could arrive either from the interrupt handlers, or can come from event handlers themselves. And then whenever there is an event, whichever one is in the front of the queue, that its corresponding handler gets called. So what it lets you do is write event-driven type systems. One additional thing, it provides some niceties. So for example, I can also give it periodic handlers. So I can say, I have this function, run it every second. What do you think it does under the hood? What if you were writing this operating system, how would you provide this kind of abstraction that run this thing every so often? Or let me rephrase it. Could you convert it into the event-driven model that could I have an event and this is the handler for it? Where would you get that event from? timer. So most CPUs, most microcontrollers have some timer hardware. So what this operating system does is it grabs one of those timer for its use, okay? And whenever handlers are given to it, which are supposed to run at specific time, it just manages that timer accordingly, okay? So my example, it will arrange for that timer to send an interrupt at the appropriate time, and then the handler gets called. So there's a lot of nice sort of wrapping around kind of the basic event-driven concept where you can expose these kind of capabilities, periodic handlers, handlers which are tied to external events and things like that. So the periodic stuff, it's called the pole handler. So that's the stuff which is repeatedly kind of called. Nice thing about Contiki, which is what has made it very popular, is that it has full support for a TCP/IP stack. Okay, using the so-called IPv6, which is kind of the latest internet protocol stack with lots of addresses, but it has a specific variant which is optimized for tiny devices so that you don't carry a lot of bits. Like IPv6 addresses are how many bits?
128.
128 bits. Okay, so if I'm carrying source and destination addresses, that's 256 bits. That's a lot of bytes. You don't want to carry those things. Okay, so so there exists a specific profile for tiny devices, and what they do is, conceptually speaking, they kind of compress it. Okay, and the way they kind of compress it is they kind of negotiate. Like if I'm talking with you with the base station, and so I can just tell you that, from this point on, this header corresponds to a particular code word, and then I will just include that code word every time, and then you can reconstruct the header. I'm kind of mutilating the exact structure code a bit, but so there is something called IPv6 LoWPAN, which is IPv6 designed for short-range wireless stuff, and this Contiki supports that. So you install Contiki, and if you are running on one of their supported platforms, literally your little device is on the internet. Okay, you can ping it, you can do whatever you want. It obviously needs to talk to, because the radios which are used out here are not Wi-Fi, so you would need some sort of a bridge device, which would kind of a gateway. But other than that, I mean, you are a full-blown part of the internet. Now, the complication also comes from the fact that most of our internet still is transitioning from IPv4 to IPv6, so usually there will be additional complexities at the gateway, but otherwise, I mean, if you're running it at your home and all, I mean, you can just ping and kind of log into or really address each and every individual sensor or actuator. Another nice capability, and this is a point which also important, most tinier embedded operating systems have a model where whenever you make a change, you have to reflash it. So like take the example of embed, you write a new program, you download it, and then you reset the thing. I don't have the they don't support this notion, my system is running and I send it a new program, okay, and then let it run. So firmware changes are all or nothing, as in I have to kind of really rewrite a big part of the firmware other than the bootloader part. What Contiki provides support is that you can actually load and unload programs within it, load and unload applications within that. This is a relatively rarer capability in embedded operating systems where, again, as I said, you reflash the whole firmware, whereas here they can load tiny parts of a new application within this. So it basically means if I have something deployed out there, it can keep doing what it was, and I can send it some additional code. Okay. Not necessarily terribly important in most applications, but sometimes this capability is quite useful. And to make this thing happen, so now remember, we don't have memory management out here. So so each program, each piece of code really does need to know where in memory it is located, and its jump instructions and all those instructions in the assembly code have to reflect the actual physical address. So to make this thing happen, Contiki does the equivalent of what normally your compilers do when they, or specifically what are called as linkers do when they assemble code into a big running executable. So there is some functionality within part of Contiki which takes an incoming piece of code and say, okay, so this code was written assuming that it could start from address 0, but I have to put it at address 100. So it actually goes through the code, modifies pieces of the assembly code to put it at address 100. This kind of relocation of the code to sit in the right place is something that it takes care of. So Contiki has this structure. Now, deep down, as I said, it is event. But actually, it plays kind of a nice little trick to give you also threads on top. But these are not real threads, these are fake threads. But they get some of the nice capabilities that that one would that threads provide. So let's take an example. Let's say I were to be writing some code. Okay, so let's some event code where my handler may look like this. Okay, I have an event coming in, and depending upon type of the event, I may do different actions. And this is just a function call. I exit. Next time the event comes in, again I kind of go through the same process. Or another one on the right. The thread version of this thing in Contiki looks like the following. I still am writing an event handler, except that I'm going to write it like a thread. So if you notice out here, at the top, I looked at the type of the event, and then I went through depending upon which event it was, I kind of handled it differently. But in any given run, they are going to happen in a particular sequence. Like, for example, I may initialize and then handle and then clean up. So my code actually is very linear. But since I'm always entering from the top, I have to do this kind of a switch thing. What Contiki does is it provides some macros. So what I do is I write a begin thing, and now here it has this. So PT stands for proto thread. So it's a thread package. It says wait until I get the event packet received, because that's the first event that I care about. Okay. Now, since it is a fake system, what is happening is my function will get called anytime any of the events are happening that I'm interested in. Okay, so I'm interested in 3 types of events: packet received, packet transmitted, and packet received and packet transmitted. So anytime either one of these happens, I will get called, except through this macro, what it is doing is it will wait here until packet has been received. So if it was an event which is not of the type packet received, then whenever I get called, I'll immediately exit here. But if the event is of this type, then I will proceed to the next one. And now I say send reply, and then I say wait until packet transmission has been done. This reflects the fact that my radio may take some time for the packet to go out, so I have to wait until I know it has gone out. And then I go into wait until the next packet is received, which is some sort of acknowledgement. And then if the packet that I receive is an acknowledgement, then I let go of wherever I had deposited the packet. Otherwise, I don't quite remember the logic out here, then I'm sending kind of an event to myself. So each one of these things is waiting for an event or sending an event, but it's a very linear code. Whereas if I were to write it in a classical approach, then I would sort of basically look at the type of event, and then each case I would handle things differently. People oftentimes do not find this logic very appealing because you have to mentally trace what sequence the events would come. Whereas here it is clear that I'm first waiting for received, then for transmitted, then for received. Arguably, and I kind of often in more complicated situations, I think it's certainly true, this makes the intent behind the program clearer. Okay, what sequence are things going to happen? Whereas here, looking at this code, you really don't know, are all possible permutations of these events possible, what would happen. Okay, so you have to kind of know a lot more about the program. So this proto thread is a magic that through some tricks of C language, Contiki and other packages like these kind of make it happen. What happens is when you give this thing to the compiler, it actually converts it into a code which looks like this, okay, with some additional sugaring thrown in. But it gives me the illusion that as if my program is starting, when the event comes, I'm kind of starting from here. I'm not entering from the top. So it's a little bit like a coroutine structure. It is actually a coroutine. So proto-thread was not Conteki's invention. It's an existing package which they adopted. It's a concept which came out of a researcher at Bell Labs who kind of found that C language has some interesting characteristic which lets you give this illusion that my function can start somewhere, enter somewhere in the middle.
Excuse me, if the compiler transferred from this type to another type, I guess there is one advantage of the first type that while waiting I can bow down as here I'm executing something and so switch.
No, remember what it's an event-driven kernel, right? So all that's happening is whenever the event happens, it calls a function. So in either case, this function is getting called, this function is getting called. The only thing is in this case, I have to look at the event and decide what needs to be done, okay, and then make sure that if the event is not the one I was currently interested in, then I handle it appropriately, okay. I go whatever, return immediately. Here I have the illusion that at this point I'm basically saying I'm waiting for packet received. Anything else comes, ignore it.
Yes, and I can bow down.
Hmm?
I can bow down until such interrupt can come.
I can power down. Okay, that's OS's responsibility. Okay, so you don't want either one of these to worry about it, right? Because I cannot power down here also because it could be that some other event may come for some other handler. So it's the kernel which has to do that. It would basically say, I'm going to power down, and because I know that the only events which come are from interrupts, for example. That's the so my event queue is empty. Then that means that only thing I could be waiting for is something coming from hardware. And therefore, at that point in time, you can shut down the processor and arrange for an interrupt to wake you up. So, but the kernel should be doing it. You cannot do it because you don't know what the other handlers are. So you cannot do it here. So Conteki has this proto-threads. There are some limitations on it, like you cannot make function calls from inside proto-threads and all. But so I think it's a little bit of a gimmicky feature, but if one really wants to have things, it can. This is another example of proto-thread where I'm writing a thread, and then I could say, forever do the following: start the timer, wait until when the timer finishes, and then restart the timer and all. If you were to try to do this thing in a standard event-oriented paradigm, you would have a handler for timer expired. You will have and this flow of logic. The fact that I'm repeatedly doing this and all will be lost. All you will see is some handlers tied to some events. So proto-threads give you on top of events kind of a interesting sugar coating to feel like you're doing thread programming. Okay, embed. So this is the one which we are using in this course. So embeds are so it started out as something totally independent of ARM, but then ARM adopted it a year and a half or two ago. It became open source. So at this stage, kind of. So when it originally started out, it had exactly one platform behind it. Now, if you look at its page, it probably has around 30 or so platforms behind it. So it's become very popular. Every vendor who has an ARM-based microcontroller basically provides support for this at this stage. So what ARM did is that they actually defined an API for operating systems to interact with hardware. Okay, so the idea is you want to make operating systems portable so that they can work across any ARM-based platform. So, so basically, this embed OS or embed package is built on top of that particular API. It's built on top of what is called an ARM CMSIS API. And then on top of on this, then it provides various capabilities. So like they had drivers for USB, networking, a whole bunch of sensors, actuators, all those LEDs, these kind of things and all. And then there is also a real-time operating system. which is our thread-based kind of an operating system. But you don't have to use this. So if you don't use this, then what you really have is kind of an event-driven system, which is there. That by event-driven, I mean it's more like foreground, background with multiple interrupt handlers. So you can write interrupt handlers and then you write the background code. That's at its essence what embed package is, but then you could use the RTOS library on top of it. So if you peek down into embed, what it really has are the following. So I have the microcontroller hardware. This is kind of bare hardware. On top of it is running this CMSIS, which is ARM's standard way of defining the API. Kind of the idea is it shields everything above from the intricacies of the specific ARM processor. You can change ARM processors within certain limits. And so on top of it, what embed does is embed defines a HAL HAL stands for hardware abstraction layer. So this is also a very common thing in operating systems, that you try to abstract away the hardware so that your operating system is mostly portable. Now, this HAL speaks this API. So the reason embed does this thing is because embed also wants this thing to be able to run on potentially non-ARM platforms also. So by creating its own HAL, it basically provides an additional level of transparency. Okay. Then what you have is sort of set of embed modules, but finally there's this thing, the embed API, which is what you deal with. And then RTOS and packages and all those kind of things are written kind of on top of that. So CMSIS stands for Cortex Microcontroller Software Interface Standard. So first thing is it's really defined for the Cortex class of ARM processors, which is the low end of processors. So what it, as the name says, it's a vendor-independent hardware abstraction layer for Cortex M series. So any tons of companies who buy the Cortex M series designed from ARM, and then all of them would work with this. So main components of these things are, firstly, it provides interface to a whole bunch of processors, M0, M0+, M3, M4, so on and so forth. There is also a DSP extension to it, because some of these processors, like the M4, have some DSP instruction sets also. And then it also provides API to support real-time operating systems. What that means is things like threads and stuff like that and all exist in this. So pictorially out here, it kind of shows the decomposition, but kind of the main idea is your application code does not sits on top of something which is CMSIS compliant. So there may be real-time kernels, there may be device drivers. These are provided by third parties, so like embed provides this in our particular case, but rest of the stuff wrapping is defined by CMSIS. Embed's memory model. So it's a single chip microcontroller that's in this class of systems. They have two kinds of memory. There's a flash memory and there is a RAM. Flash memory is the larger one, usually of maybe 32 kilobyte, 128 kilobyte, so a few tens to a small number, let's say a megabyte type thing. It's non-volatile. This is where you store program instructions, and this is where also what you store are all the constant data values. You generally, from within your program, will only read these values, although you can write to it, but it's a costly process. So for example, on the board that we are using, flash is 256 kilobyte. Now, writing to it is a slow process, partly because the way writing to flash memory works. Anyone knows what's funky about writing to a flash memory? What's weird about it relative to a normal model of memory?
Compared to what?
Compared to normal memory, like normal memory, want to write to a memory location, I just write to it. Yeah, so the problem with flash memory is the following: it's organized into blocks or called pages, and I can only write page at a time. So if I want to modify a location, I have to, in a sense, read it and then rewrite the whole thing. Okay, so it's a very expensive proposition. The other thing is flash memory ages. So each block has a finite number of write cycles that it comes with, usually 100,000, 200,000, something like that. And after that, it becomes useless. Now, a lot of this stuff is hidden from you by hardware on the chip, But the main point is you cannot use it like RAM where I'm maintaining, I don't know, like every time my clock tick happens, I write stuff to it and all. So like, for example, your idea of maintaining a log will probably kill my flash memory in no time, okay? This doesn't have that lifetime. So you cannot, so it's meant primarily for reading, okay, not for extensive writing. RAM is the volatile memory, which I can use like a traditional memory. I can use it to store variables, stack, heap, all these kind of things that I'm used to. The only problem is it's very tiny, 32 kilobytes. Okay, my program resides in Flash because that's where I'm running from. Strictly read only, and only time when I rewrite the program do I go there. My file system can reside there, but you have to be careful that you're not writing much too frequently, and be aware that it's a slow process. RAM is where the fast stuff happens. You cannot put code in the RAM. You cannot put code and run off that, and it will not give you any benefit anyway. This is where you put the data. So in C, so that's the hardware view. The view from a software perspective is that any program, and those of you in CS are probably very familiar with it, that really three regions of memory. Okay, one is a stack. Every time I make a function call, I push state into the stack. I put variables there. When I'm done, I kind of pop out of it. Each thread will have its own stack. If I have a single thread, that is, I don't have multiple threads, then there's a single stack in the system. Heap is what is used for dynamic memory allocation. This is where whenever I say create a new structure, malloc or new, depending upon your programming language, that's where it goes. And then finally, I have global or static memory. These are variables that are allocated upfront and are inexistent through the life of the program. So this would be stuff which I put at the top of my file, declaring variables outside any function. These are so-called global variables which are always there. Or even, in my example, the static index inside a function would have also gone into the global static memory. So, and this memory is guaranteed to be appropriately initialized. So even if I just set static int x, this initial value would be 0. That's guaranteed by the programming language. So what this diagram below shows is that how things get organized. Remember, this is my hardware view, and this is kind of my software view. So there is the RAM, there is a flash. In the flash, I would have the program part as well as the data which was supposed to be here, because it needs to be appropriately initialized. Like, for example, I might have said somewhere at the top of my program, int y equal to 3. That's in my code. So when the program begins to run, that stuff has to be there. So it's also in the flash. It's part of the binary file that my compiler outputs or you download. And the bootloader, the first thing it does is it copies this data into the RAM, because we don't want it to be sitting out here because it needs to be writable, and writing to flash is very expensive. So it copies all this data into the RAM. Okay, so that's what's happening out here. This stuff got copied out here. Okay, and my stack will go downwards from here. There is this area of memory which we initialize with 0. Okay, and excuse me. So read-write data goes out here. We initialize this area with some value. Stack goes down, grows down from here. If I have a heap, I may have a structure like this. I put read-write out here. I have the 0 initialized, and then the heap, which is where I put my dynamically allocated data structure. One thing you see is that I grow in this direction, whereas stack grows in this direction, because you want to give stack maximum flexibility. So like whosoever wants to use kind of the middle space gets to use it. If the stack grows more than the heap, sort of it will come down from here. The thing to keep in mind is all of this is sitting in a single address space. So for example, if inside my function I were to say allocate an array of 20 kilobytes, well, that data structure will go onto the stack, a huge amount. And then if I write to it, I'm going to end up crashing my heap or even this part of the memory. And there's no protection against it, okay, because the hardware is incapable of doing it. So things can crash. One very commonly, so there are a couple of things you could do. One is maybe you have access to some tool which analyzes your program and makes sure that it will never be the case that your stack will grow this much. Not easy to do. Normally these kind of tools are not there. So there is another trick which is often done, not foolproof, but the idea is that I will write some specific pattern into this middle zone. Okay, so maybe a very unique pattern. Okay, and then if the stack trashes it, then I would know that it got trashed. Okay, so maybe like for example, I'll put FFFFFF there or whatever, some particular pattern. And then if the stack grows into it, then it will overwrite some area, and then I can detect whether the problem was because stack overflowed or something else. Okay, but that's kind of a basic model. Flash program continues sitting in the flash. The flash binary in the flash also had this initial data, which gets copied into the RAM, and then depending upon whether you have the heap or not, sort of you're going to use some part of that. The RTOS and embed, it's actually based upon an operating system called RTX, but ported on top of that particular RTOS API. So it provides you threads. And this is very much like the thread model I described earlier. I have threads which are ready to run, threads which are waiting for something, some hardware resource or something, and then I will have a thread which is actually running, and then threads which have been temporarily deactivated. Okay, so I can make a thread active or inactive also. But otherwise, a very classical one is preemptive. So basically, the kernel looks for events from event handlers or other threads, and then based upon that makes the scheduling distinction. It has support for what are called as mutexes or mutual exclusion software. So anytime I have a shared resource, like for example, let's say I have a radio in which I have to send the packet, but act of sending that packet takes a few different calls. One thread is using it, I want to lock out the other thread. So mutex does that. Think of it like a lock thing. I can lock a resource and then I can unlock it so that two threads will not trash each other on that. So that's the second thing they provide. Then they provide semaphores. Semaphore is something which is built on top of lock, and it basically has something about it has, if I have multiple of a resource, then I can do it. So let's say, for example, let's say I have a buffer, or what's a good example? I have an area of memory where I can put 5 elements, okay? And any combination, one thread can put 5, or one can put 4, and the other can put 1, or whatever, okay? So there is a capacity to my resource. So in this case, what would happen is a thread would ask for the resource, and if there is a spare resource in there, there is remaining capacity, it will get it. If not, it will have to wait. So you can think of mutex being nothing but a semaphore which is only for one capacity of 1. Semaphore is something more than that. So that's the next thing that they provide. Then they have signals. Signals is like events that threads can send to each other. So for example, I may have a thread which can signal, which can send a signal, so this thread is sending a signal whose value is 1, and this thread is waiting for the signal with ID 1. Okay, so you can have threads kind of talk to each other. It provides queues. So a message queue, a thread can put a value into the queue, and the other thread can pick up from the value. So these are very common ways for threads to interact, and Mbed RTOS provides all of them. And in that regard, it's very typical of a lot of operating systems that you'll find. They also have a notion of mail. So basically, so the difference between queue and mail is the following. In queue, whatever data I'm sending, I have to put it into the queue, and it can only be a small type of data. But let's say I'm sending an image, a big blob of data. Then in case of mailbox, what I do is I put the pointer to my blob out in the queue, and then the blob is sitting separately. And then this guy, the recipient, when it gets the blob, its responsibility is to kind of free it up. So it provides timers. So within the system, I can say start a timer, restart a timer, wait for a timer, those kind of functions it provides. And finally, it lets you write interrupt service routine. So if you add a new hardware which is talking to an interrupt, so embed has pins which can correspond to interrupts, or maybe you are using some peripheral which is on the chip, again, you can write the interrupt service routine, and then that interrupt service routine can generate events and all for the rest of the system. So embed RTOS, basically these are kind of features, and you don't have to use all of them. Like maybe your system could be very simple. It just has a single thread, so you don't spawn off any threads. In that case, all you are really doing is you are basically writing interrupt service routines and handling events. So that's embed RTOS. Then, so we looked at Contiki, we looked at embed RTOS. Embed RTOS is more sophisticated. It has threads, real threads. Contiki does not. But you can always use embed RTOS the way you would do Contiki, namely just as an event-driven system. What Contiki does have, which embed RTOS doesn't, which is a whole TCP/IP stack, which really makes it very useful for IoT type applications where these things are getting networked. On the other hand, what embed RTOS has going for it is a very rich set of platforms. I mean, if you look at the web page, they have like 30 platforms, and there's a whole bunch of like drivers and all people have written, whereas Contiki supports a very small number of relatively expensive platforms, and that's what it is. So it's not a very rich, it's not very rich in hardware diversity. Embed is very rich in hardware diversity. Both have big communities around them. Embed is more popular worldwide, I would say. Contiki is a little bit more of a European focused thing, but again, sort of a lot of industry uptake on that. So depending upon your application space. One other thing is Contiki comes with a very good simulator. So you can actually emulate your entire embedded platform before deploying, which embed doesn't have an equivalent. Moving up, real-time Linuxes. So I mentioned that how there are commercial OSs with real-time extension. So standard Linux kernel has very large footprint and is non-real-time. So it's neither embedded nor real-time. So two directions Linuxes have evolved. One is that there is version of Linux which can work without MMU. So these are very small footprint Linuxes, and they don't assume an MMU to be there. So everything runs in the same address space, but you get the benefit of full TCP/IP stack. So you can do networking and all. That's kind of one thing which holds back a lot of people in embedded OSs is that you're designing a product and it needs to hook up to the cloud. And you need a good, robust TCP/IP stack, and typical embedded OSs, Contiki being an exception, don't come with one. So in embed, for example, you can send Ethernet packets, but that's it. They did not provide a TCP/IP stack for it. So very rare, or at least until recently, it used to be fairly rare that embedded RTOS, they were basically designed for standalone applications, not for networking. So that's where the traction of Linux was coming from. And then, of course, you have a whole bunch of other things, other languages and all that get supported in the Linux. So Micro C Linux was a small footprint Linux. It came about in late 90s, and this was actually written to run on Palm Pilot. So when Palm Pilot had come out, people were interested in running Linux on it. It had a processor which didn't have a MMU, so they wrote Micro C Linux to kind of work on that, and so since then it has been there. There are extensions on standard Linux which give you soft real time, and they target audio-video applications. So audio applications have always been very sensitive to timing. So there is a library in Linux called ALSA library. I don't know if any one of you, these are called ALSA drivers. This is what your sound cards and all use, even on desktop. And so there was some support for timing that has always been there in standard Linux, but we're a very targeted thing just for sound drivers, and to some extent also on video. More relevant are the true real-time Linuxes. And there are many approaches to it. Some of them basically patch the kernel. Some of them layer things on top of it. So let's talk about, so there, I'm skipping a few slides. Okay, so one class of approach out here is what is called as compliant kernel approach. Okay, so the basic idea out here is that I take the Linux kernel and then I modify it so that I can support real-time applications. Okay, so I literally, every time a new Linux kernel comes out, I kind of go around patching it, kind of creating a real-time version, and I maintain the same Linux system call API, but then I kind of enhance it in some ways to begin to support some of this real-time capabilities. But I benefit from kind of the rest of Linux ecosystem. So there are several releases of Linux which are kind of like that. But there are limitations to what you can do, and of course there are kind of other ramifications that come up. A more different approach is taken by RT Linux and RTAI, and what they do is the following. On top of hardware, I run a real-time system. Okay, this is some real-time operating system that they created. My real-time tasks run on that, and my entire Linux kernel runs at one of those tasks. Okay, so it's kind of a weird sounding approach, and then Linux processes run on top of that Linux kernel. Okay, so now what happens is, unlike here, where I had to patch the Linux kernel very extensively all over the place, and then here I basically keep the real-time tasks separate. They get truly hard guarantees, and then the entire Linux kernel is, or in fact, you might imagine multiple Linux kernels, if you are so inclined, are kind of running on top of this base operating real-time operating system. What would I need to change out here to make this magic happen? Come in.
The way the kernel itself, the stock kernel actually interacts with the hardware. So like you have to abstract those hardware calls, the health system, the API calls, the interrupt handlers, mechanisms.
Right. So really, kind of the main thing is that Linux kernel is also interacting with the same hardware as these guys are. By hardware, I mean devices and interrupts and things like that. So I'll have to make sure that those are handled correctly. For example, let's say my UART sends me an interrupt. Where does it go? Okay, should it go to should it be delivered to the Linux kernel or not? Okay. The other thing is that the code in the Linux kernel, which would otherwise directly talk to the drivers, to the hardware, now needs to talk to something out here. Okay, so this guy has to give it an illusion as if it's talking to hardware. Okay, so that's kind of the approach done. But this is, like I said, a couple of companies have adopted this thing. This approach is pretty commonly kind of used. There is a final one, which is the following. What they do is they take it's a little bit like sort of previous approach where I replace the Linux kernel with. So here, what happened? I took the Linux kernel, I put my own kernel which supported the Linux API and also the real-time stuff. What we do out here is we take the Linux kernel, but add some additional modules into that kernel which provide real-time capabilities, and they also expose an extended API, which can provide some additional capabilities. So this is an approach taken by a version of Linux out of CMU, again commercialized, called TimeSys Linux. So they take, again, standard Linux releases, but you kind of inject some additional real-time stuff to it. The nice thing there is, one of the things they are able to do it is that in addition to real-time, they also actually provide support for other type of resources. So like, for example, you can say some process gets 10% of the radio, another one gets 50% of the radio. So you can not just CPU time, but also other resources like radios and memory and all could also be similarly treated. You can schedule things that way. So this TimeSys and Linux RK are kind of examples of that. You could, for example, say one thread could say reserve a core for me because I really need it. Okay, so you can begin to reserve resources which are in your computing system. You can reserve entire chunks of DRAM. You can sort of expose some power management capabilities and stuff like that. So these are various variants of Linux RK. What I've found myself in practice is they're a bit of a pain to use a normal usage, in the sense there are a lot of caveats around it, tie-ins with specific hardware platforms, just generally not something where you, unlike Linux, standard Linux, you can download, compile, install. They tend to be a little bit tricky to handle. Final one when it comes to embedded Linuxes, and probably the most popular at this stage, is Android. So Android is Android OS, as we call it, is really something which is on top of a Linux kernel. An entire Java-based thing that Google has created, in which they provide support for various things, including sensors. So there's a whole sensor manager kind of stuff in Android, which gets exposed. Now, this is my last slide out here. The reason I'm not going to go into depth into this thing is next Wednesday, my student Chengwang Shen is going to give a lecture on Android, its architecture, and how you develop an app for it. So he's kind of going to walk you through that. I think probably, I mean, at this stage, arguably, Android is the most dominant embedded operating system, okay, because you're seeing it, people are using it in standalone devices, televisions have it, and also I think getting exposed to its architecture is interesting. And the thing is, you're no longer really dealing with Linux. It's under the hood, hidden. You're really dealing with kind of a layer on top, which is the Android OS. It's not real time, really, but it has some shades of it. Like, for example, when you're talking to a sensor, you can basically say, I'm interested in, like, Android gives you options for a few different latencies or rate. Okay, so you can exercise some control over the timeliness, but not to the same extent that a hard real-time system would do. So it's not really designed for that. But we're seeing a lot of appliances, home gateways, these kind of things have begun to use Android, and I think getting to see its architecture a little bit would be interesting, because it does some very interesting games to make all of it work in a very memory-starved setting. Okay, I mean, you really don't have a whole lot of memory even on your smartphone, all things considered, relative to, let's say, your laptop and all. So it does a lot of interesting games out there, but basically when we think of Android OS, what it really is, on top of Linux kernel, there's a runtime, which is the Java-based virtual machine, or Talzik virtual machine, which actually in Android 5.0, which just got released, has been replaced by something called ARB, Android Runtime. So there is changes there. There's a whole bunch of libraries which include libraries on top of which sit the counterparts in the application, which are called the managers. There are within this thing, I don't think I show it out here, but there's a library, something which corresponds to sensors, for example. Okay, it kind of manages all the sensors. And there's a counterpart object on the application side which lets you interact with the sensors. So that's kind of interest to us. But then also the magic which kind of goes on in here is kind of also interesting, the way it handles it. So next Wednesday, Chengwang is going to cover that. On Monday, I'm going to go into some scheduling, real-time scheduling.